All right, welcome back, Academic Astronomy. I hope everybody's doing really, really well. I'm sitting here drinking my coffee from my Pittsburgh Pirates mug, and I guess one of the only real positives about this lockdown is Major League Baseball season is still postponed, so the Pittsburgh Pirates are not yet in last place. So I guess we got that going for us. Back behind us, you can see the big boards. We still got our Astronomy Madness tournament going on. So if you haven't joined the Astronomy Madness Google Classroom, please consider doing so. We've had a ton of upsets, whole lot of drama going down. And of course, you can find this and all of our Astronomy Madness videos on the YouTube channel. So today we're going to be taking you through part 2 of the section 7 notes on stars and galaxies. So this is going to cover pages 5 through 8. And so if you do have a PDF of the notes, please have that open, or even better, if you have the notes printed out, it's real easy to follow along because today you are going to be filling in some blanks. So let's go ahead and get started. And at the very end of this, I'm going to ask you 10 questions that are going to appear on Google Classroom, and you're welcome to use your notes to answer them. So last time where we left off, we were talking about the HR diagram, the Hertzsprung-Russell diagram, probably the most awesome diagram in all of astronomy. We use it to classify stars essentially based on 2 things, their brightness and their temperature. So today, we're going to be referring back to that diagram as we start to talk about our star family in space. Remember, stars are not actually living, breathing things like you or I, at least as far as we know. But we're going to talk about them that way because it makes it easier for us to understand what stars are like. So our first group, which you might recall was across the top of the HR diagram, are supergiants. And right away, we're in for a little bit of a surprise. You might think because they're larger that they're actually older stars, but supergiants are actually newborn or baby stars. They are very young overall, and they were just born really, really big. So if we go to fill in these blanks, for overall magnitude, that means brightness. If you have your notes printed out in front of you, notice everybody, whether blue or red, the supergiant bubble is always across the top of the HR diagram. So for overall magnitude, we would write very bright. Now the overall temperature actually depends on what color the star is. The blue variety of supergiants, you might notice they're in the upper left-hand corner, are going to be very bright and they're going to be very hot. But the red flavor in the upper right corner is going to be very bright, but it's going to be very, very cool. So these are young baby stars, and we're going to see overall they're very young because when we learn about the deaths of stars, they do not live very long at all. Very short lives, in fact, as short as only 2 million years. So some examples that we've had in class, Sirius the dog star at the head of Canis Major would be a blue-white supergiant. Vega in Little Lyra the Harp, which should be high overhead near the zenith this summer, is a blue supergiant. And then the real whoppers are the red supergiants, like Antares, the heart of the scorpion, or Betelgeuse in the shoulder of Orion the hunter. These red varieties can get up to about 2,000 times larger than our own sun. So were you to take Antares or Betelgeuse and put it in our solar system in place of the sun, the entire inner solar system out through Mars, poof, just immediately engulfed inside that massive star. So our next group are giant stars. So maybe at this point you're thinking to yourself, okay, it's kind of weird that really big stars are young. So giant, that sounds big, right? They must be really young, right? Wrong. Giant stars, I like to call grandparent stars. They do get rather big like supergiants, but we're going to see that they live their lives totally differently. Their stellar evolution takes place in a different way. So if you can take a minute to find this bubble on your HR diagram from the previous page, notice that the bubble is actually over to the right and it's below the supergiant region. So for our overall magnitude, instead of saying very bright, we can simply say bright. It's a little bit above the 0 magnitude line right in the middle, so they are bright. And for the temperature, they are going to once again be cool because they're over at the right side. Remember, all red stars are relatively cool. Some examples we have of giant stars would be Aldebaran, the reddish eye of Taurus the bull, and then Arcturus, which we are about to get to in the springtime sky, which is actually the 5th brightest star in the sky, and it's at the feet of Boötes the herdsman. In fact, Arcturus is so bright that sometimes when I'm out observing in the spring, I have to double check just to make sure I'm not confusing it with the planet Venus. It's so very bright. We are going to see a little bit later on that yellow main sequence stars like our sun will become grandparent stars and giants someday. So let's talk a little bit about our sun. By far, everybody, the most dominant star group on the HR diagram are the main sequence stars. I like to call these the moms and dads, or sons and daughter stars. They are young to middle-aged stars. Most of them are yellow like our own sun. Remember, a common theme here through section 7 is our sun isn't all that special. It's actually just a regular, average, ordinary run-of-the-mill star. If you look on your HR diagram, you'll see that this bubble stretches from the upper left to the lower right. And it contains, for that reason, the hottest and coolest stars ever found. So understand there's an amazing range of properties here with the main sequence. The stars in the upper left would be very bright and hot and mostly blue. The ones down in the lower right, which we'll talk about a little bit more in depth soon, would it be very, very cool and very dim and very red. So for our overall magnitude, we've got quite a range here. I think we could write V bright to V dim for very bright to very dim. And for our overall temperature, we could write V hot to V cool, very hot to very cool. Lastly, notice everybody that actually 90% of the stars within our sky that we can see fall within the main sequence. Even think about your own family. Some of you might have a grandparent that got too old to live by themselves, so they've moved in with you. Some of you might have a newborn at home. But probably most of your family is you, your brothers and sisters, and your parent or parents. Same thing for the main sequence, and a perfect example is our sun, Sol. All right, moving on to the next page, let's get to the last main star group that we have on the HR diagram, and these are our dwarf stars. Now, I like to call these the great-grandparent stars because they can actually get even older than giant stars. In fact, in just a little bit, we're going to see that main sequence, giant, and white dwarf stars are all inexorably linked together. But here we have 4 color varieties, and the bubble that you see on your HR diagram usually just refers to white dwarfs. So these are about the size of Earth or smaller. They're hot core remains of stars that actually take place when a red giant swells up and then poof, blows off its outer layers into space. Technically, there's no sound in outer space, but that's how I imagine it sounding, just a poof. This is not a kaboom like a supernova, it's just a poof. So here, because they're in the lower left, their overall magnitude is going to be dim. Notice they're down at the bottom of the HR diagram. But the overall temperature is going to be hot because they're over at the left-hand side. By the way, I'm never sure in this video whether my left and right reverses for what you're seeing. So if I ever say left and I point the wrong direction, Mr. Krug does know his left and right. I'm just not sure how you're seeing it at home. So for a moment, it might seem kind of odd to think that a hot star is dim because you'd normally think that hot stars are really bright. But understand, everybody, for white dwarfs, it's more because of how small they are. Because they are so very small, they're not giving off a lot of light, even though they themselves are very hot. Now, our next group, initially, you're not actually seeing on the HR diagram, or are you? These ones are called red dwarfs, and they are actually somewhat of a subgroup on the bottom end of the main sequence. And surprisingly, they represent the most numerous, longest living stars in our universe. You might remember from day 1 of these notes, I mentioned that the human eye is actually a little bit biased towards color. Our eyes can pick up blues and whites far better than longer wavelength, lower frequency colors like orange and reds. On top of that, red dwarfs are very, very small, so they're very difficult to see. In fact, as far as I know, there are no red dwarfs visible to the naked eye from here in the northern hemisphere. And I don't even believe there are in the southern hemisphere as well. Yet, if we could see all stars equally, there would be more tiny red dots on the sky than anything else. So even this HR diagram, which I found online, I think it's quite a good one. Technically, if we were also relating quantities of stars, there would be way more little red dots down in this corner, making a huge pile than anywhere else. So their overall magnitude, because they're way down at the bottom, is going to be very dim, and their overall temperature is going to be very cool. So these are cool, dim stars. And surprisingly, they live a very, very long time, which initially might seem surprising to you, because you might think to yourself, well, wait a minute, if they're small, they won't have very much fuel, so they'll probably burn out quickly. But it's almost like they know that they don't have a lot to start. So these stars are going to use their nuclear fuel very, very sparingly. Astronomers estimate a red dwarf could live anywhere from 20 billion up to 200 billion years. And when you think that the age of our universe, as far as we know, is about 13.7 billion years, these are little tiny stars that could theoretically live beyond our current universe many, many times over. Just one quick alien angle for you because it's kind of fun. The most commonly reported extraterrestrial life form that people claim they see today is, of course, the so-called gray alien, the creepy little ones with the big black eyes. I did watch a special one time where some evolutionary biologists took a look at what people describe they actually see. And they looked at it very objectively, and they said, if there's a chance a life form like this could have evolved around another star system, then it's likely it may have actually happened around a red dwarf, because there would be much, much lower light than we enjoy around our yellow main sequence star Sol. So there, having good eyesight would definitely be favored in low light conditions. And over time, that could cause eyes of living beings there to grow a lot larger. Kind of a cool take on extraterrestrial life. Okay, our last two color varieties might surprise you because neither actually shows up on the HR diagram. Because to be on the HR diagram, you have to give off heat and light. That's why we don't see a lot of planets or moons on the diagram, because they just shine by reflected light from our sun. So we have black dwarfs and brown dwarfs. And so even though the colors sound pretty similar, these are actually separate things. So we don't want to mess them up. Black dwarfs, we will see, are basically stars which were once alive but then died out. So a star, after it poof, blows off its outer layers, will linger on for another few thousand or million years as a white dwarf. But once it finally runs out of nuclear fuel, it basically just fizzles out. And so stars like this, and like our sun someday, as we learned on day one, will fuse the whole way up to carbon. And so a black dwarf is essentially a floating dead charcoal briquette floating in outer space, not unlike the charcoal that your mom or dad might have on the grill outside, but much, much denser. In fact, one time years ago, I read an article where a team of astronomers thought they found a black dwarf that may have actually crystallized, which, kind of exciting, ladies. That means somewhere lurking out there, there might be a single diamond as big as an entire planet. So those are black dwarfs. And sadly, it's the fate of our own sun someday, billions of years from now. But hopefully by then, humans will have advanced to the point that we are colonizing many, many other star systems. Now, in contrast, we have brown dwarfs. And if you did watch my extra credit lecture from Marking Period 3 on the legend of Planet X or Nibiru, this is where we talk a little bit about brown dwarfs. Black dwarfs are like stars that were alive but since died. Brown dwarfs are like stars that were never actually born. And you can see here, I've added a diagram of the planet Jupiter, which some people consider a brown dwarf. So what's our sun made of? Hydrogen and helium. What are planets like Jupiter and Saturn made of? Mostly hydrogen and helium. So if Jupiter had gotten a few times more massive, it would have actually begun nuclear fusion at its core, and it would have become a star as well. So now we could classify it as a large planet, or some might say a small brown dwarf. As we also learned, brown dwarfs can be rather dangerous because some of them aren't bound to solar systems, and they're sort of just floating out there in the abyss of the cosmos. And so since they're not generating their own light, the only way we could really pick them up is by their infrared signature, is even planets like Jupiter do give off a little bit of heat in their core. Okay, so if you ever take a standardized test, here in Pennsylvania, Keystones or the SATs, or in elementary school, the PSSAs, sadly, astronomy is woefully underrepresented. But if they ever ask you one question about astronomy, it's almost always on stellar evolution. Do not be intimidated by the term stellar evolution. It just simply means how stars live throughout their lives and how they change. So, will every star go through every single stage? Will every single star be a supergiant, giant, main sequence, white dwarf, red dwarf, brown dwarf, black dwarf? The answer is no. Stellar evolution is going to depend on a star's mass when it's born. So this next diagram, I'll try to show you a little bit piece by piece. And I think this is the second most awesome diagram we have in the notes after the HR diagram. And this is kind of a homemade diagram from Mr. Krug, but you can find very similar ones online. So let's go through this. All stars, whether they are born big or small, begin in similar ways, in stellar nurseries or molecular clouds or nebulae. Here you can see almost all of M16, the Eagle Nebula, in its entirety. You might recall on page 1 of the notes, I showed you a zoomed in picture just of this area right up here. Sometimes astronomers refer to this as the pillars of creation. And you can see little bumpity bumps, little protostars forming all through these towers like olives on the branches of a tree. So first, everybody, let's head down the high mass chain. You're going to see, despite the enormous size of these stars, they are going to chew through their nuclear fuel very ravenously, and this chain is very short, violent, and chaotic. So supergiant stars, blue or red, are not going to live all that long. What ends up happening, everybody, is they're fusing heavier and heavier and heavier elements in their core until they fuse the whole way up to iron. Iron just happens to be the one element on the periodic table that we know of that you cannot fuse for more energy. It actually costs a star energy. It loses energy if it tries to fuse iron. So as they're growing, this core of a fuel that they cannot use is also growing inside them. It's almost like they're killing themselves from the inside. And that seesaw we talked about on day 1 between gravity and star energy precariously starts to wobble. And then in one split second, gravity wins out and crushes the star and flips the seesaw. This implosion then creates a tremendous kaboom called a supernova. And it's one of the biggest explosions in the universe. To give you some idea of the magnitude of a supernova, in one split second, a supernova will give off more energy than our sun will during its entire 10 billion year lifetime. So just try to ballpark all the energy that our sun gives off every second of every single day. Add all that up over 10 billion years, and a supernova is still that much more powerful. In fact, this is kind of terrifying. If a star would ever supernova within 30 light years of us, it would basically fry the Earth as the wave of radiation hit our little planet and stripped off our ozone layer. But do not fear this. There are no massive stars within 30 light years of us that are going to supernova anytime soon. There's only one potential type of supernova that might get us, and it's still a long shot, and we'll talk about that one a little bit later. Now, despite being such an intense impact, we were talking about a core of solid iron here. So sometimes the core can survive. Now, at this part of my diagram, you'll see some astronomers diverge a little bit on what happens. Some consider this 2 different end states. Some put them in more of a straight line. I sort of separate them. If the core is just sitting there, not really spinning rapidly, we would call that a neutron star. It's called this because during the intensity of the explosion, all the free little protons and electrons combine to make neutrons. And this would be a star of what physicists like to call degenerate matter. This is literally matter that is packed together as tight as the laws of physics will allow. That's what actually stops the collapse, because for a time it can't get compressed anymore. This is actually so dense that astronomers estimate that a teaspoonful of a neutron star would outweigh an entire mountain on the Earth. Now, if the star begins to spin, it will give off radio pulses like an old police siren or a lighthouse beam. Pulse, pulse, pulse. And that is called a pulsar. If you look at these two diagrams, notice they both have a neutron star at their hearts. But the pulsar, because it's spinning, is giving off radio waves. A little more on pulsars in just a bit. Now, it seems like, at least to me, that the high rotational velocity of a pulsar can hold off a collapse. But the neutron star, everybody, gravity can overpower the seesaw one last time and crush it and implode it to form one of the most mysterious and powerful objects that we have in the cosmos, the black hole. We're going to talk a lot about them and their weird effects on the next page. But for now, simply know that black holes are called black because their gravity is so strong that not even light, the fastest thing in the universe we know of, can escape. So this entire chain that we see on the left side, everyone, the high mass chain, from start to finish, it could be as short as 2 million years. Now, in contrast, let's talk about the right-hand side. This is going to be our average or our low mass chain. And right here, everybody, is where our sun is now. We are essentially at the first step. We are a main sequence star. Our sun has been at this step, astronomers estimate, for about 5 billion years, and we think it has enough fuel left in the tank. It could probably be here for at least another 4 billion more. So the events I'm about to tell you about, do not panic. You're not going to go outside this weekend and look up and see our sun starting to change, but it is coming someday. So what's going to happen to our sun someday? Well, eventually our sun is going to run out of hydrogen to fuse, and inside its core, it's going to be amassing a lot of helium. For starters, the sun will begin to contract until the leftover hydrogen and some of the helium starts to ignite and makes a second fusion shell. When this happens, that seesaw between gravity and star energy, for the first time in our sun's life, will actually start to teeter towards star energy. And our sun will begin to grow outward into what is called a red giant. In fact, someday, if our distant descendants, or the robots who eventually take over all humans and rule the Earth, if they cannot find a way to physically move the Earth away from the sun, our sun will grow big enough to actually engulf the planet whole. But do not fear this. Even though this is still billions of years away, astronomers and physicists already have at least one idea on how they could actually move the Earth away from the sun. Maybe more on that a little bit later. So red giants keep getting bigger and bigger and bigger until they poof. They just kind of blow off their outer layers in a poof. And this, everybody, is called a planetary nebula. Now, this is a little bit of a misnomer. That means a deceiving name. It actually has nothing to do with planets. But when earlier astronomers started to spot these through the first decent telescopes hundreds of years ago, a lot of them looked like little bluish-greenish disks like planets. So the name stuck, even though it has nothing to do with planets at all. Now, one thing I didn't mention on the high mass chain, notice I have added what I call 2 recycling arrows here, one after supernova and then one after planetary nebula. What's left after a star blows up or blows off its outer layers? A cloud of gas and dust. What are stars made of? Clouds of gas and dust. So in this way, this is why you teens should be recycling at home. Even Mother Nature recycles as well. In fact, quick aside for you, we actually see this within our own sun. When astronomers look at the spectra of our sun's soul, the unique light fingerprint our sun gives off, they can actually see that our sun has traces of iron in it. But that's kind of weird, right? Because our sun, as we now know, never gets big enough to actually fuse iron. So where did the iron come from? Well, it turns out our sun is actually somewhat of a second generation star, which astronomers somewhat confusingly call a population 1 star. So the first generation, oddly called population 2, were basically a wave of massive supergiant stars earlier in our universe's history. They got very, very big. They kaboom, blew themselves apart in a supernova. And then all that iron and other material got scattered through the cosmos. And then new stars like our sun eventually rose from that, like a phoenix rising from the ashes. And so they have bits and pieces of those original stars left over. So as the famed and popular astronomer Carl Sagan loved to say, we are truly made of the stuff of stars. So right now, all of the iron coursing through all of the veins in our body at one point was actually forged in the nuclear furnace of a massive star. So let's go ahead and finish out the low mass chain now. Notice everybody at the center of the planetary nebula, almost like a bullseye, we have a little white dot. You may have guessed it. This is where our white dwarf comes into play. So after the red giant poof and blows off its outer layers, we have that little white hot core left over. That's a white dwarf. You might notice a kind of ominous arrow pointing over here to supernova explosion. There is just one time the small mass star can actually supernova. It can happen to a white dwarf, and we'll talk about why just a little bit later. Finally, this is where our last dwarf type comes into play. The white dwarf will burn on more or less quietly for hundreds of thousands to even a few million years until it burns out, and that would be a black dwarf. So this entire chain where our sun is, from start to finish, for a star like our sun, might last 10 billion years. For a smaller red dwarf, might actually be 200 billion years. So you can see stars live their lives very, very differently. Okay, I think we have just one page to go here before we start the questions. Thanks everybody for sticking with me. So let's quickly review the deaths of stars. So first off, stars like our sun. Near the end of a long life, that seesaw between gravity and star energy starts to teeter back and forth. So when gravity is stronger, the star gets smaller. When star energy is stronger, the star gets bigger. So bigger, smaller than just a poof. It peacefully blows off its outer layers in a planetary nebula. This is where matter can get recycled. Now on our last lecture, we're going to see there's actually a couple different types of nebulae, about 4 or 5. But here I'm going to keep it very simple. We're going to talk about just 2. Basically nebulae that are giving off light, either because they have stars inside them or because their gases are actually so excited they're making their own light at the atomic level. Those are called diffuse nebulae. And then clouds of gas and dust where there's no light are called dark nebulae. You might recognize this one. This is probably the most famous or second most famous dark nebula out there. You might recall this is the Horsehead Nebula, and it's found below the far right belt star, Alnitak, in Orion the Hunter. So here, both types of nebulae are in beautiful display. The dark tower that is shaped like the head of the horse, that would be our dark nebula. And the only reason we can see it at all is think about it 3-dimensionally. We have a diffuse nebula lit up back behind it. So those are stars like our sun. Now, high mass stars. Near the end of a very, very short life, maybe only a couple million years, which for stars is actually just the blink of the eye in the cosmos, they are left with this unfusible iron core. The seesaw immediately tips towards star energy. The whole star gets crushed. This implosion creates a tremendous kaboom, a massive explosion called technically a type 2 supernova. Now notice we have a vocab term that we haven't seen in a while here, Big Bang. I just included that because understand, this doesn't mean that we can look at pictures from deep space and every single place we see a cloud of gas and dust, we can say, aha, that must be where a star died out. Our universe, even at 13.7 billion years old, is still young enough that there are actually still clouds of gas and dust left over from the original Big Bang that have simply never formed stars. So clouds of gas and dust are created when high or low mass stars end their lives, but that doesn't mean every single one we see is an X marks the spot where a star died out. So you might recall the iron core can survive, and that is called a neutron star. If it starts spinning, though, it gives off radio pulses, and that is a pulsar. Now, why did I put this image of creepy little gray aliens here? Well, a little bit of astronomy history. When the very first pulsar was discovered, the team of astronomers who found it were very, very excited. And they tentatively dubbed it LGM, which actually stood for Little Green Men. So what do astronomers in the SETI program, Search for Extraterrestrial Intelligence, what do they sometimes look for on the sky? They look for a patterned radio signal as evidence of communication of extraterrestrial life. What does a pulsar give off as it spins? Pulse, 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 a patterned radio signal. So my guess is they may have been a little bit disappointed to find out it really wasn't aliens, but they were probably still very excited because they found a brand new object that previously was not known to astronomy, and that is a pulsar. So finally, a little bit of story time here. If gravity overpowers the neutron star again, it can collapse one last time, and that can form the mysterious, the powerful black hole. So interestingly, at least 2 different teams of astronomers actually predicted black holes would be out there before they found any of them. And I believe this actually happened 2 different times. First, it actually happened after the time of Isaac Newton. Isaac Newton, somewhat of a precursor to Einstein, had figured out the equations for orbital or circular velocity and then escape velocity, which the Apollo crews needed to reach to break free of the immediate gravitational pull of the Earth and journey out to the moon. Escape velocity, even for little tiny Earth, is about 25,000 miles per hour. That's why when any of us jump up, we always come right back down, because none of us can jump fast enough to actually escape from the gravitational pull of the Earth. So anyway, these astronomers, these physicists figured out if you made an object massive enough but small enough, its escape velocity would actually be higher than the speed of light, which was known with relative certainty by the early 1900s. So basically, you could have an object of almost infinite mass where things would go in but could not get back out. Then, into the second or third decade of the 1900s, after Albert Einstein had published his epic work on general relativity, which, if you look at this diagram down in the lower right, you might recall from section 4 of our class. This is where very large masses like planets, moons, and stars, and even black holes can physically warp the fabric of space-time. They basically rediscovered this same concept. If you made a singularity of almost infinite mass, it could essentially warp the fabric of space-time so much. The walls would be so steep that not even light could climb back out of them. So it's kind of fascinating that using the work of Newton and Einstein, people were able to predict black holes would be out there before they ever found any of them. And because their mass so warps and contorts space-time around them, really odd things can happen, potentially even time travel. So the boundary of a black hole is usually called the event horizon. And it's called that because we cannot see any events happening inside of it. Because if you cross that boundary, your escape velocity would then exceed the speed of light, which you would need to get back out of it. So astronomers are somewhat divided on what the event horizon might look like. The most recent photographs that have come back appear to show it as just a black void. But some astronomers think up close it might actually look like a mirror ball or like a disco ball that would reflect all the light outside around it. So let's say, just to end our lecture today, that you and your friends were exploring the outer boundary of a black hole sometime in the future, or somewhat like the movie Interstellar with Matthew McConaughey. As long as you stay outside the event horizon, you might be just fine. But let's say one of your friends gets a little bit bold and he or she actually wants to cross over the horizon to see the inside of the black hole. And you beg and plead, you say, no, no, don't go. But your friend persists and they cross over the event horizon. Now, what they would see versus what you would see would diverge significantly at that point. For your friend, initially they wouldn't feel much different. but they would become the first human in history to see the inside of the black hole. Some physicists think it would be pitch black. Others think it might be very, very bright because so much light is captured inside. The problem is your friend couldn't tell the rest of you across the boundary on the other side what it actually looked like. If he or she turned around and tried to tell you, as soon as the sound waves left their mouth from the words, they would get pulled back into the black hole. Instead, if they tried to take a picture with their cell phone and then turn and show you the screen, as soon as the light came off of the screen, it too would get sucked down into the black hole. If they went in feet first, they would get stretched out like a Gumby towards the center or the singularity. If they went in head first, they would get stretched out like a cone head. And all this stretching of your poor friend would heat him or her up millions of degrees, and sadly, they would get incinerated before they ever got close to the singularity. Now, for all of you outside the black hole, you would never witness your friend's demise. What you might see, physicists tell us, is essentially a ghost image of your friend frozen in time on the boundary of the event horizon. So if he or she went across the event horizon like this, you would basically see this image frozen for well over a century long after they were gone. And then it would gradually just get dimmer and dimmer and dimmer until it would eventually disappear. So because of this, some physicists like Ron Mallett have actually speculated this might be a future source of time travel. Instead of actually plunging into the black hole, you could basically orbit your ship around the outside of the black hole, where time itself has almost ground to a halt, and then shoot away from it. And that might actually induce time travel as well. Okay, thank you all for listening to lecture number 2. Let's start going through our 10 questions, which you're now going to see in Google Classroom. And remember, you are allowed to use these notes to help you out. And this assignment is not locked, so you can pause the video at any time to really take your time to find out the answer. And just so we don't get confused, these questions I am going to number 11 through 20. 11 through 20, that's how you'll see them. So here we go, good luck. Question number 11. This star group of newborn baby to young stars are consistently very high magnitude, but are very hot or very cool depending on their color. So what is the term for this group of newborn or baby stars? Feel free to pause this video and answer question 11. Question 12. This group of stars is also large, but arrived at this juncture much later in life. Informally known as grandparents, they are bright but cool, and most are red. Question number 12. Okay, number 13, simple math question. If 90% of stars are part of the main sequence in a random sampling of 40 stars, how many would be within the main sequence on average? So 90% of stars are in the main sequence. We have a sampling of 40 stars. On average, how many of those would be part of the main sequence? Question 13. Okay, questions 14 and 15 I call Dwarf Destiny. Number 14, Dwarf Destiny. This color of dwarf star are actually on the bottom of the main sequence and are the most numerous, longest living stars in the universe. Number 14. Dwarf Destiny. Never getting massive enough to jumpstart nuclear fusion, these balls of gas and dust lurk silent and dark, not giving off any visible light of our own. These are stars which were never born. Number 15. Number 16. Examine the stellar evolution diagram in our notes. Remember, teens, this is the diagram where we had the high mass chain and the low mass chain. In what environments are all stars, whether large or small, born? In what environments are baby stars born? Number 16. Number 17. This chain of our star life cycle is very short, violent, and chaotic, and can end, kaboom, as a pulsar, neutron star, or black hole. Name that chain. Number 17. Number 18. Stars like our sun are not massive enough to supernova at the end of their lives. Instead, they will poof and blow off their outer layers in a low energy explosion called a what? And remember, this was a little bit of a misnomer, a deceiving name. What is the name of this lower energy explosion? Number 18. Number 19, pulse, 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 pulse. Because of their pulsating radio pattern, astronomers who discovered the first pulsar initially thought they may have found what? Number 19. And finally, number 20, fill in the blanks. Black holes are called black because their blank is so strong that not even blank can escape. Number 20. All right, teens, thank you very much for sticking with me. That concludes the second lecture of our Stars and Galaxies notes. As you might guess, there's just going to be one final lecture so we can take you through the rest of it. I hope that you've enjoyed it so far. And for those of you that actually did listen to the whole thing, rather than just fast forwarding to the end and trying to wing the questions, I really do appreciate that. So go ahead, if you haven't done so, please answer 11 through 20. And don't forget, looking back at our big board, Astronomy Madness Round 2 will be back very, very soon. Stay tuned and stay safe.